Good morning, all. Today we are going to discuss about electric dipole in the first chapter of electrostatics in the 12th portion. Two equal and opposite charges, their magnitude is equal. Q equals Q. Only difference is that one is minus, other one is positive. Two equal and opposite charges separated by a small distance constitute an electric dipole. The main property of an electric dipole is electric dipole moment. The electric dipole moment is always represented as P. P is equal to one of the charges Q, only magnitude of charge we are taking, into distance between the two charges 2a. See, dipole will be like this, minus Q plus Q. Distance between this is taken as 2a. Until midpoint it is a, this point also it is a. Total distance will be 2a. The dipole moment is defined as product of one of the charges and the distance between the two charges. The unit of electric dipole moment is Coulomb meter. Whenever you write the unit of electric dipole moment, you should be very careful. Write C as capital, M as small letter. Otherwise, you'll measure it as centimeter. So please avoid that. Then, you know the direction of electric field. Direction of electric field. The direction of electric field is from positive to negative. We have studied electric field lines. It starts from positive and ends at negative. So the direction of electric field is always from positive to negative. But the direction of electric dipole moment is from negative to positive. The direction of electric dipole moment is always from negative to positive. The direction of electric field is always from positive to negative. Now, some of the examples in our common life for the electric dipole is water. Water process electric dipole moment. The electric dipole moment is given as, or it happens because the center of negative charges, negative charge and positive charge are slightly separated. See, on the hydrogen side we have positive, on the oxygen side we will be having negative charge. There will be a slight distance between this negative charge and positive. So water process electric dipole moment. So we can consider water as an electric dipole. Another example is ammonia. Ammonia also possesses electric dipole moment. Next, we are going to discuss about what happens when electric dipole is kept in a uniform electric field. See, we are having two charges, minus Q and plus Q. Minus Q and plus Q, they are separated by a distance 2a. due to this charge, a force is acting. The force will be acting in this direction. See, the force here is in this direction. Here, minus Q, the force will be in this direction. This two forces, QE and minus QE, cancels each other. So net force, the net force acting on the dipole is 0, because this is a uniform electric field. One force is acting in this direction, other force is acting in the opposite direction. Net force is acting in the two opposite directions. Now see, the two forces are acting on two different points. Plus QE is acting at the point B, plus QE is acting, minus QE is acting at the point A. Two equal and opposite forces acting on two different points constitute a couple. See, inside the electric field, negative charge, positive charge, it is kept like this. It is kept in angle theta. So this angle also will be theta. A, B, this point is taken as N. Now, here a couple comes. The couple always tries to rotate the dipole. See, plus QE is in this direction, minus QE is in this direction. Plus QE is acting in this direction, minus QE in this direction. Two equal and opposite forces gets cancelled each other, but since they are acting at two different points, a couple is acting here. Example for couple, when you are opening a pipe, you are applying a couple on the surface. When you are driving, two equal and opposite forces are applied. That also constitutes a couple. Now here these two forces constitute a couple. Couple leads to rotational motion. Whenever there is a rotational motion, there is a torque. Torque 2 equals force into perpendicular distance. Here force is QE into perpendicular distance is AN. This is the perpendicular distance between the two forces. Perpendicular distance between the two forces. Now torque tau equals QE into, here this distance is 2A, we already know. This is hypotenuse, this is opposite side. We can write here it as AN is equal to 2A sine theta. Because hypotenuse is 2A, AN is opposite side. We can write sine theta equals opposite side AN by AB, which is equal to AN by 2A. Cross multiply. You will get AN is equal to 2A sine theta. Then we can write QE into 2A. This can be written as Q into 2A into E sine theta, which is equal to Q into 2A is P, E sine theta. Torque tau is equal to P sine theta, or we can write tau equals P cross E. Whenever the dipole is in the same direction of electric field, theta equals 0. Whenever the torque, or sorry, the dipole is in the same direction of the electric field, theta equals 0, then torque is equal to 0, because sine 0 equals 0. Whenever the dipole is perpendicular, theta equals 90 degree, then the torque becomes P sin theta is sin 90, tau becomes maximum. So maximum torque is acting on a dipole when it is kept perpendicular to the electric field. Next is we are going to find out electric field along the axial line. Here it is plus Q, here it is minus Q, equal and opposite charges. P is a point at a distance R from the center. We need to find out electric field at the point P. To find the electric field, first of all, we consider first EA. EA due to this charge, EB due to this one. Then we will take the difference between these two. Then we can find out the net electric field here. See, for minus Q, distance is R plus A. Here it will be R plus A, because R is here, from here to here R, then plus A. For EB, it is R minus A, because only this distance we have to consider. The electric field due to minus Q charge is acting towards A, but electric field due to plus charge is acting in the opposite direction. Say minus Q plus Q. Now here we are having the point P. From the center, the distance is R. This is A, this is A. Now EA, this point is A, this point is B. EA equals 1 by 4 pi epsilon naught Q divided by R plus A the whole square. Note down, here it is R plus A. EB equals 1 by 4 pi epsilon naught Q divided by R minus A the whole square. Now EA and EB we got. Next, but EA is in this direction, but EA is in this direction and EB is in the opposite direction. EB is greater than EA. Now, total electric field E equals EB minus EA. This will be equal to 1 by 4 pi epsilon naught Q by R minus A the whole square, because EB is in this direction, minus EA will be in the opposite direction. 1 by 4 pi epsilon naught Q by R plus A the whole square. Here 1 by 4 pi epsilon Q can be taken outside. 1 by 4 pi epsilon naught Q into 1 by R minus A the whole squared minus 1 by R plus A the whole square. Now, see, one by 4 pi epsilon naught Q, that is already taken out. R minus A into R plus A the whole squared upon r plus a the whole squared minus r minus a the whole squared. This can be written as 1 by 4 pi epsilon naught q into r squared plus a squared plus 2ar, expansion of this part, minus r squared minus a squared minus of minus plus 2ar divided by r squared minus a squared the whole squared. This can be written as 1 by 4 pi epsilon naught q into r square cancels, a square cancels, 2ar and 2ar together will come as 4ar divided by r squared minus a squared raised to 2. This will be equal to 1 by 4 pi epsilon naught. Here we can written as q into 2a into 2r. This 4ar I am splitting as 2a into 2r divided by r squared minus a squared the whole squared. 1 by 4 pi epsilon naught q into 2a is p into 2. So we can write as 2pr divided by r square minus a square the whole square. If a is very much negligible, a very much less in comparison to r, then we can write E is equal to E is equal to 1 by 4 pi epsilon naught. 2pr is there. 2pr divided by a is neglected, r raised to 4. R square raised to 2, that is r raised to 4. So we can write E is equal to 1 by 4 pi epsilon naught. R and R cancels. 2p by r cubed. This is the relation for electric field intensity along the axial line of a dipole.